When you think about natural disasters, the mind often jumps to chaos, to unpredictability, to forces so powerful and random that they feel almost malicious. But here's something that might surprise you. Beneath all that apparent chaos, there's actually order, there's pattern. There's something almost calming about understanding how these events work, how they follow rules that scientists have spent decades mapping and studying. The forces that shape our planet aren't random acts of destruction. They're fundamental processes, ancient mechanisms that have been operating for billions of years before humans walked upright, and they'll keep operating long after we're gone. What makes this topic genuinely relaxing isn't ignoring the power of these events. It's understanding them. It's recognizing that these disasters follow patterns, that we can predict where they'll happen, that we've learned to build in ways that protect us from them. Natural disasters are Earth's way of maintaining balance, of redistributing energy, of keeping the planet functioning in a state that supports life. They're the machinery that makes the world work. And once you understand that, once you see the order beneath the violence, something shifts. The fear doesn't disappear entirely, but it makes room for something else. Curiosity, respect, appreciation for the incredible forces that shape our world. A kind of peace that comes from knowing how things actually work, from understanding that the ground beneath our feet and the sky above our heads operate according to comprehensible, discoverable principles. That's where the relaxation comes from. Earthquakes are the planet breathing. Deep within the Earth, the ground is never truly still. Even though we experience solidity and stability when we stand on it, the ground moves constantly, measured in centimeters per year, shifting and adjusting as the massive plates that make up the Earth's crust grind against one another in an ancient, ongoing dance that has continued for billions of years. This movement happens because of forces operating deep beneath the surface. The Earth's interior generates heat from the radioactive decay of elements within the planet's core and mantle. This heat creates convection currents in the viscous rock far below, causing the plates to float on top of a shifting layer called the mantle. It's a beautiful system actually. The heat rises, the rock moves, the plates shift, and over millions of years, this process reshapes the entire surface of the planet. Mountains form, ocean basins open and close, continents drift across the globe. When you understand plate tectonics, you understand why earthquakes happen where they happen. The plates move slowly, typically just a few centimeters annually, but that movement is constant and relentless. Where these plates meet, where they press against one another or pull apart, tremendous stress builds up. The rock resists this movement at first. Friction holds the plates in place even as the deeper forces keep pushing, keep pulling. Stress accumulates silently, invisibly, building for years or decades or centuries. And then, at some point, the stress becomes too great. The friction can no longer hold the plates in place. The rock breaks, the plates slip, and that sudden movement releases energy in waves that travel through the earth. That's an earthquake. It's not an anomaly or a failure of the system. It's the system working, doing what it's designed to do, releasing stress that would otherwise continue to accumulate until it becomes dangerous. What's genuinely fascinating about this mechanism is how it creates a kind of pattern, a rhythm, a predictable cycle that repeats over and over through geological time. The stress builds gradually, year after year, the plates pressing against each other with increasing force, the rock being slowly compressed or stretched or sheared. The plates move suddenly, the stress is released, and then the cycle begins again. In places where plates interact frequently, like certain coastal regions and island zones, this means earthquakes happen regularly, sometimes many times per year. Small ones mostly. The tension releases in smaller increments, rather than building up to one massive release. And here's where it gets genuinely relaxing. There's an inverse relationship between the magnitude of an earthquake and how often it occurs. The more earthquakes a location experiences, the weaker those earthquakes tend to be. This is not a coincidence. This is not random. This is how the Earth manages stress. Think of it like popping small bubbles of pressure regularly, rather than letting them accumulate until there's an enormous explosion. A location that experiences frequent small earthquakes is actually safer in the long term than a location that has been quiet for a century or more, because that quiet location might be accumulating massive amounts of stress that could eventually release in one catastrophic event. Places that experience frequent, moderate earthquakes are actually experiencing a stress relief system working perfectly. The ground is shaking regularly, yes, but those regular tremors prevent the kind of catastrophic pressure buildup that could create a massive, devastating earthquake. The stress is being released continuously in manageable increments rather than building to a breaking point where the release is violent and dangerous. This is the Earth regulating itself, maintaining equilibrium through the continuous release of energy. The plates converge in some regions and produce compression stress. In others, they diverge and produce tension stress. In still others, they slide past each other horizontally, creating shear stress. Each type of stress produces different kinds of earthquakes with different characteristics. But the underlying principle is the same. Stress builds. The rock can only hold so much. Release follows inevitably, always. When plates converge, one plate often gets pushed beneath another in a process called subduction. The stress builds as the sinking plate encounters resistance. The friction between the two plates is tremendous, but it's not infinite. When enough stress accumulates, when the force from the deeper mantle convection becomes strong enough to overcome the friction, the plates suddenly slip. That slip releases energy in waves that propagate through the rock in all directions. When that stress finally releases, the shock can travel through the rock and water, sometimes creating tsunamis. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake near Sumatra, was generated by this exact process. A massive subduction zone earthquake caused the sudden uplift of the sea floor, which displaced a huge volume of water and generated waves that traveled across the entire Indian Ocean. But most earthquakes never touch the water. They happen entirely within the crust, releasing their energy through ground motion alone. And that's actually less dangerous than it sounds. Modern buildings can be designed to withstand significant shaking. Engineers understand the mechanics of how earthquakes work. They know how to distribute forces, how to design structures that flex rather than crack, how to use materials and techniques that absorb seismic energy instead of transferring it catastrophically through the structure. Seismic isolation systems, dampers, flexible connections, reinforced frames. These engineering solutions come directly from our understanding of how earthquakes work and how energy propagates through structures. What makes understanding earthquakes truly calming is recognizing that there are places where earthquakes almost never happen. The vast majority of Earth's land surface is nowhere near a plate boundary. Stable continental interiors, places far removed from any plate boundary, experience earthquake activity so infrequently that major earthquakes might occur only once every few thousand years, if at all during recorded human history. You can live your entire life in a location where significant seismic activity is incredibly rare, where the ground beneath your feet is statistically one of the safest places on Earth. And even in places where earthquakes are common, the scientific understanding of plate tectonics has made prediction far more precise than it used to be. Scientists have mapped the major fault lines around the world. They understand which regions are at higher risk. They monitor ground movements constantly with sensitive instruments that can detect even tiny tremors. These sensors are land-based, placed at strategic locations around known fault zones. Additional instruments are placed aboard satellites, aircraft, and stationary buoys floating in the world's oceans. All of this data streams continuously into research centers where scientists analyze it, looking for patterns, looking for changes that might indicate increasing stress, looking for the subtle precursors that sometimes appear before major earthquakes. This data is assembled into global maps showing earthquake patterns, revealing which regions are most active, which fault lines are most dangerous, which areas are overdue for activity based on historical earthquake recurrence intervals. Engineers and urban planners use this information to build safer cities, to locate critical infrastructure away from the highest risk areas, to design structures that can withstand the stresses we know will come. Modern building codes in earthquake-prone regions require specific engineering practices. Flexible foundations that allow buildings to move without transferring all that motion to the structure itself. Reinforced frames designed to redistribute forces. Materials that can bend without breaking, that can dissipate energy rather than transmitting it rigidly through the building. Engineers understand how earthquakes transmit energy through structures, and they design buildings to absorb that energy rather than resist it rigidly. The Ring of Fire, the zone of intense tectonic activity around the Pacific Ocean, where roughly 90% of all earthquakes and volcanoes occur, is actually a source of comfort in some ways. It's a defined region. We know where the danger zones are. We know why they're dangerous. We can monitor them. We can prepare for them. We can build resilient infrastructure there. We can focus our resources on the regions where they're actually needed. Billions of people live in areas far removed from the Ring of Fire and its associated seismic hazards. In those places, earthquake risk is so minimal that it barely factors into planning or everyday life. Perhaps most reassuring of all is understanding what happens after an earthquake. The plates don't stop moving. They continue their slow drift, their constant adjustment. But immediately after a major earthquake, the stress in that particular region drops dramatically. The pressure that was building for decades or centuries has been released. The rock has settled into a new configuration. In many cases, it will take a very long time for stress to build back up to the point where another major earthquake occurs in that same location. This is called the earthquake cycle. The cycle is simple in concept, but profound in implication. Stress builds slowly and continuously. An earthquake happens, releasing the accumulated stress suddenly. A period of relative quiet follows, as stress begins building again from zero. Large earthquakes are often followed by periods of relative quiet, in terms of major seismic events, sometimes lasting decades or even longer. The system has released its tension. It's moving into a phase where the next shock is still distant. This is profoundly reassuring if you think about it. A major earthquake, while frightening at the moment it occurs, actually brings stress relief to the system. It represents the completion of one cycle and the beginning of a new cycle where stress levels reset. In regions with documented earthquake histories, scientists have used this understanding to estimate how long the quiet period might last. A region that experienced a major earthquake 50 years ago might not experience another for 100 years or more. This knowledge can provide comfort to people living in those regions, knowing that a major earthquake in their area is not imminent. Meanwhile, the aftershocks that follow a major earthquake are typically much smaller than the main event. They decay in frequency and magnitude over time. The energy released by the main earthquake has already dissipated most of the accumulated stress. The aftershocks are the final adjustments, the small shifts as the rock settles into its new stable position. They're like the system catching its breath after exertion. Scientists monitor these aftershocks carefully because they provide information about the structure of the fault and the way the earthquake redistributed stress across the region. Modern earthquake warning systems now give us the ability to detect earthquakes within seconds of their occurrence and issue alerts to people in areas that will experience strong shaking. When an earthquake happens, seismic waves emanate from the epicenter at different speeds. The fastest waves, called P waves, arrive first but cause less shaking. Slower waves, called S waves, arrive later but carry most of the destructive energy. Modern systems detect the P waves, calculate the earthquake's location and magnitude almost instantaneously, and send out alerts before the more damaging S waves arrive. This window, sometimes only seconds long, can be enough to allow people to take protective action. Drop, cover, hold on. Get away from windows, move away from shelves that could fall, move away from the coast if a tsunami warning has been issued. Get to higher ground. These actions, taken in the seconds between the arrival of the warning and the arrival of the strongest shaking, can save lives. Studies have shown that early warning systems provide measurable, meaningful protection to people in earthquake-prone regions. The technology works. The systems work. We have the capability to give people advance notice so they can protect themselves. This is a triumph of applied science, a concrete example of how understanding natural processes allows us to reduce suffering and save lives. For centuries before plate tectonics, earthquakes were a mystery. They seemed random, unpredictable, terrifying, acts of God or nature with no explanation and no way to prepare. But we've solved that mystery. We know how they work now. We know why they happen, where they happen. We know that they're not random at all. They're the inevitable result of physical processes operating on a planetary scale. We understand the stresses that build at plate boundaries. We can measure the rate at which those stresses accumulate. We can estimate, based on historical records and geological evidence, how much stress typically builds before an earthquake is released. This knowledge doesn't mean we can predict exactly when an earthquake will occur with precision down to the day or hour, but it does mean we can identify regions where earthquakes are likely and monitor those regions carefully. Knowing this doesn't eliminate all risk, but it transforms our relationship with that risk. We're no longer helpless in the face of earthquake activity. We're informed. We can prepare. We can build resilient infrastructure designed to withstand the shaking we know will come. We can position ourselves in locations where earthquake risk is minimal if we choose to. We can design early warning systems that detect earthquakes within seconds of their occurrence and alert people to take cover before the strongest shaking reaches them. We can organize evacuation drills so that people know what to do when an earthquake warning arrives. The earth moves beneath our feet, constantly, invisibly mostly. But that movement follows rules. It has patterns. It's comprehensible. It's not chaotic or random or beyond our ability to understand. And that comprehension brings a kind of peace. We live on a dynamic planet. Earthquakes are part of that dynamism. They're not aberrations. They're not signs that something has gone wrong. They're simply the Earth doing what the Earth has always done, constantly reshaping itself, adjusting its surface, maintaining the balance of forces that keeps the planet functioning as a system for billions of years. Volcanoes are the Earth bleeding. Where earthquakes represent the mechanical stress of moving plates, volcanoes represent the thermal energy of the planet's interior trying to reach the surface. Deep within the Earth, temperatures are hot enough to melt rock. This magma, molten stone under extreme pressure, seeks pathways to the surface. When it finds a weakness in the crust, when it encounters a crack or a fissure, where the rock above becomes too thin or fractured to hold back the pressure any longer, it rises. The magma forces its way upward through the rock layers, following the path of least resistance, finding the easiest way through to the surface. Sometimes it finds a weakness created by plate tectonics. In subduction zones, where one plate is pushed beneath another, The friction and heat can melt the rock, creating magma chambers that eventually feed volcanoes. In rift zones, where plates pull apart, the decompression of the mantle rock allows it to melt, creating magma that rises to fill the gap. In hotspots, columns of hot material rising from deep within the mantle create volcanic activity that slowly drifts across the surface as plates move over these stationary plumes of heat. The mechanism varies, but the principle is the same. The Earth is hot inside. That heat needs to escape. Volcanoes are one of the primary mechanisms through which that heat exits the planetary system. Without this heat loss mechanism, without the ability of the planet to release the thermal energy generated by radioactive decay in its core, the entire system would become inhospitable. The oceans would boil. The rocks would de-soften. The entire plate tectonic system would break down. Volcanoes, in this sense, are essential to maintaining the conditions that allow life to exist on Earth's surface. What's remarkable about volcanic activity is how concentrated it is geographically. Just like earthquakes, volcanoes are not randomly distributed across the planet. They follow the plate boundaries and the hotspot trails, the same fundamental features of plate tectonics that create earthquake zones. Roughly 90% of the world's volcanoes are found in the Ring of Fire, that same zone where 90% of earthquakes occur. This concentration means that volcanic risk, like earthquake risk, is actually quite geographically limited. Enormous areas of the world have virtually no volcanic activity at all. You can live your entire life in locations where volcanic eruption is a virtually non-existent threat. This geographic concentration is actually a huge source of comfort because it allows resources to be focused on monitoring the regions where volcanoes actually exist. For people living in volcanically active regions, the scientific understanding of how volcanoes work has become incredibly sophisticated. Scientists can identify the signs that a volcano is becoming more active. They monitor ground deformation, using instruments that can measure millimeter-scale changes in the shape of the volcano, detecting the subtle bulging and shifting that occurs as magma rises toward the surface. They track gas emissions, analyzing the composition of gases being released from the volcano, because changes in gas composition often signal changes in volcanic activity levels. They measure temperature changes in hot springs and geothermal areas associated with the volcano. They analyze seismic activity beneath the volcano because the movement of magma and the fracturing of rock as magma forces its way upward, produces earthquake signals that scientists can detect. They've deployed networks of sensitive GPS receivers around active volcanoes that can detect movements of just millimeters. All of these measurements together provide advance warning of volcanic activity. Sometimes the warning comes days or weeks before an eruption, sometimes longer. This advance warning period is crucial because it allows time for evacuation. Communities near volcanoes can be emptied of people before the eruption occurs. This has saved countless lives over the past few decades. The eruption of a volcano is not some random catastrophic event. It's the culmination of measurable physical and chemical processes. Magma pressure builds. Gas within the magma increases in concentration. The pressure differential between the magma chamber and the surface increases. All of these changes can be detected and measured by trained volcanologists using sophisticated instruments. Once an eruption begins, the character of that eruption can often be predicted based on the composition of the magma and the structure of the volcano. Some volcanoes produce explosive eruptions where gas and ash are propelled high into the atmosphere. Others produce flowing lava where molten rock spills down the slopes relatively gently. Some produce both depending on conditions, but the type of eruption is determined by chemistry and physics, not randomness. It's predictable in its character, if not necessarily in its precise timing. The viscosity of the magma determines a lot about the eruption. Thin, Low viscosity magma flows easily and produces gentle flowing eruptions. Thick, high viscosity magma doesn't flow as readily, and gases become trapped within it, building pressure that results in explosive eruptions. The mineral composition of the magma affects its viscosity. The temperature of the magma affects its viscosity. The amount of dissolved gas affects the pressure. All of these factors can be measured and analyzed. This predictability makes it possible to prepare. Communities near volcanoes know what type of eruption is most likely based on the history of that particular volcano. They can design evacuation routes accordingly. They can identify safe areas and staging zones where people can wait for all clear signals. They can have emergency plans in place that account for the specific hazards their particular volcano is most likely to produce. This planning, this preparation, saves lives when eruptions occur. Consider the historical record of volcanic eruptions. The eruption of Krakatoa in Indonesia on August 26, 1883, stands as one of the most powerful volcanic events ever recorded. The explosion was so violent, so energetic, that it was heard from hundreds of kilometers away. One of the loudest sounds in recorded history. The explosion and subsequent collapse of the volcano generated massive waves that reached heights of 135 feet, destroying coastal towns and villages along the Sunda Strait in Java and Sumatra, killing approximately 36,400 people. The volcanic ash from this eruption circled the entire Earth within weeks, actually cooling global temperatures for months afterward, because the ash in the upper atmosphere reduced the amount of solar radiation reaching the surface. The day became noticeably darker across much of the world. This eruption was unquestionably catastrophic in its human toll. Yet what's fascinating about it is how it demonstrates the power of volcanic processes and how it contributed to our modern understanding of volcanic hazards. We now know how volcanoes like Krakatoa work. We understand that volcanic eruptions can trigger tsunamis, that the sudden displacement of water caused by a volcanic explosion or collapse can generate waves capable of traveling vast distances at incredible speeds. We understand what caused the Krakatoa eruption. We understand what led to the tsunami. We can identify other volcanoes with similar characteristics and monitor them vigilantly. We can put warning systems in place, both for the volcanic eruption itself and for any tsunami that might result from it. If a similar eruption threatens a populated area today, we have time to evacuate 8 people to safety before the disaster strikes. This knowledge, this understanding of volcanic processes and their potential hazards, allows us to respond effectively and save lives. There's something almost beautiful about volcanic activity when you think about it from a planetary perspective. The Earth's interior is hot because of the energy released by radioactive decay deep within the planet's core and mantle. That energy has to go somewhere. If it couldn't escape through volcanoes, through the slow upwelling of hot rock at mid-ocean ridges, through the convection currents in the mantle, the planet would grow hotter and hotter. Volcanoes are part of the thermoregulation system of the Earth. They're one of the mechanisms through which the planet releases excess heat into space. Without this heat loss mechanism, the Earth would become inhospitable. The oceans would boil. The rocks would soften and lose their structural integrity. The entire plate tectonic system, which depends on the strength of the rock under stress, would break down. Volcanoes aren't disasters in the sense of being failures of the Earth system. They're features of a healthy, functioning, thermally regulated planet. They're evidence that the Earth is alive, dynamic, and maintaining the conditions necessary for life to thrive. Consider also the productive aspects of volcanic activity. Volcanic soils are incredibly fertile because they're enriched with minerals and nutrients from the magma that created them. When lava cools and weathered over time, it breaks down into soil loaded with minerals that plants need to grow. Some of the most agriculturally productive regions of the world are located in volcanic areas. Populations throughout history have recognized this and returned again and again to volcanically active regions because the soil is so rich, so capable of producing abundant crops. In Iceland, geothermal energy from volcanic heat is harnessed to provide heating and electricity to the entire nation. The hot springs and geothermal vents that dot Iceland aren't seen as purely dangerous phenomena. They're recognized as valuable resources. In New Zealand, geothermal resources support both power generation and the production of goods. Geothermal energy is renewable, it's clean, it's reliable. Hot springs fed by geothermal heat have been used by humans for centuries for their therapeutic properties. People have traveled to volcanic regions specifically to soak in these warm waters, which are believed to have healing properties for various ailments. The heat that drives volcanoes is also a resource that humans can tap into and use productively. This is a profound shift in perspective. Instead of viewing volcanic regions as purely dangerous places to avoid, we can recognize them as places that offer both challenges and opportunities for human flourishing. Historically, volcanic eruptions have shown patterns of activity over time. Some volcanoes erupt frequently, almost on a regular schedule, sometimes with intervals so predictable that scientists can actually forecast when the next eruption will likely occur. Others go dormant for decades or centuries and then erupt again. Some eruptions are explosive and dramatic, producing ash columns that reach tens of kilometers into the atmosphere, while others are relatively gentle. Others produce relatively quiet lava flows where molten rock seeps out of the ground and spreads across the landscape slowly enough that people can often evacuate and even watch the lava advance from safe distances. The variation is real, but it's also somewhat predictable based on the history of a particular volcano. A volcano that has erupted explosively in the past is more likely to erupt explosively again, given similar conditions. A volcano that historically produces slow lava flows is less likely to produce an explosive eruption. This is because the character of a volcano is determined by the structure and composition of the magma source that feeds it, characteristics that remain relatively constant through time. That doesn't change dramatically from one eruption to the next. So the volcano's behavior, in a broad sense, remains consistent over time. This consistency is valuable because it allows scientists to categorize volcanoes, to understand their likely behavior, and to tailor monitoring and preparation strategies accordingly. Modern volcanologists understand the mechanics of magma chambers, the way pressure builds, the way gases evolve within the magma, the way different minerals crystallize at different temperatures. They understand how the composition of the magma affects its viscosity and how viscosity affects the type of eruption that results. They understand the behavior of different gases dissolved in magma and how those gases come out of solution as pressure decreases, driving eruptions. They've created sophisticated computer models that can simulate volcanic behavior based on initial conditions and known parameters. These models can help predict what will happen when a particular volcano begins to show signs of activity. They deploy networks of sensors around active volcanoes that provide constant streams of data. Seismometers detect earthquakes and volcanic tremor. Gas sensors monitor the composition of emissions. Tilt meters measure changes in the slope of the volcano's surface as magma rises or falls within it. GPS receivers track deformation. Thermal cameras measure temperature changes in volcanic features. All of this knowledge serves one purpose: to predict volcanic activity accurately enough to allow people to get to safety before an eruption strikes. The goal isn't to prevent volcanoes from erupting. That's not possible, nor would it be desirable, even if it were possible, because volcanoes play such a crucial role in maintaining the Earth's thermal balance and in supporting the ecosystems and economies of the regions where they exist. The goal is to know when they're going to erupt so that people can move out of the way. The goal is to provide advance warning so that evacuation can be orderly and complete before the hazard arrives. What makes volcanoes genuinely relaxing to think about, once you understand them, is this combination of geographic concentration and scientific predictability. The regions where volcanic activity poses a serious threat are well known and well monitored. People in those regions know what they're dealing with. They have warning systems in place. They have evacuation plans. They understand the characteristics of their particular volcano and the types of hazards it's most likely to produce. They know how fast lava flows. They know how far ash will travel. They know how high tsunami waves might reach. This knowledge transforms uncertainty into preparation, fear into readiness, and people everywhere else, the vast majority of Earth's population, living far from active volcanoes, can go about their lives essentially free from volcanic threat. The volcano is not a random killer. It's a feature of geology, predictable in its locations and increasingly predictable in its behavior. It's the Earth doing what the Earth has always done, cooling itself, releasing heat, maintaining the thermal balance that allows life to exist on the surface. Understanding this transforms the perception of volcanoes from frightening anomalies to logical, comprehensible features of our dynamic planet. Volcanoes are not punishment. They're not signs that we've done something wrong or angered some cosmic force. They're not failures of the Earth system or evidence of chaos at work in nature. They're simply the inevitable consequence of a living, thermally active planet that is constantly working to maintain balance and regulate its internal temperature. The heat that erupts from volcanoes is the same heat that powers the plate tectonics that build mountains, that move continents, that shape the face of the Earth. Volcanoes and earthquakes and the slow movement of the continental plates are all parts of a single grand system, a planetary machine that has been operating for billions of years, that will continue operating for billions more. That's something to find peace in, not fear. The volcanic systems that power the planet are also systems we can predict and understand. When a volcano begins to shift into activity, it announces itself through measurable changes, a kind of geological telegraphing that gives us windows of opportunity to prepare and evacuate. Scientists monitor these volcanoes obsessively, installing networks of sensitive equipment that detect the subtle movements of magma rising through the crust. Seismometers pick up earthquake swarms, sometimes thousands of tiny tremors as magma forces its way through rock, fracturing it as pressure builds. Tilt meters measure the bulging of the volcano's surface as pressure builds from within, detecting millimeter-scale deformation that signals rising magma. Gas sensors analyze the composition of volcanic emissions, watching for changes in sulfur dioxide, carbon dioxide, hydrogen sulfide, and other compounds that signal magma movement through the subsurface. GPS receivers track ground deformation with millimeter precision, creating maps of how the volcano's surface is shifting. Thermal cameras record temperature changes in volcanic features, identifying areas where heat is increasing. Gravimeters measure subtle changes in gravitational fields as dense magma moves through rock and replaces less dense material. All of this data streams continuously to volcanologists, who assemble it into a detailed picture of what's happening beneath the surface. A three-dimensional model of magma chambers filling, rock being displaced, pressure mounting. This monitoring creates early warning. Sometimes weeks before an eruption, sometimes months, the signs become clear enough that authorities can act. A volcano is waking up. Communities that have lived in proximity to volcanoes for generations know what this means. They know their specific volcano's behavior, its patterns, its tendencies. They know whether eruptions are typically explosive or flowing, whether lava fountains or violent blasts are more likely. They know how fast lava moves in their region, how to calculate evacuation routes based on lava flow speed. They know how far ash travels, what areas will be buried in centimeters of ash versus completely covered. They know the timing, roughly how long an eruption typically lasts, how much warning they might have before an eruption begins based on the precursor signals. This knowledge becomes preparation, and preparation becomes safety. Evacuation routes are practiced regularly. Emergency supplies are stockpiled and maintained. Communities understand their particular volcano not as a random threat, but as a neighbor whose behavior they've studied and come to understand, whose patterns and moods they can read from the subtle signs of geological activity. What's remarkable is how many people live safely in volcanic regions precisely because they understand what they're dealing with. Iceland sits on one of the world's most volcanically active regions, yet it's a modern, developed nation where people thrive. Why? Because Icelanders understand their landscape completely. They know which volcanoes are dangerous. They have monitoring systems in place. They know how to build infrastructure that can withstand volcanic hazards. More importantly, they've learned to use volcanic features productively. Geothermal energy from volcanic heat powers much of Iceland's electricity. Hot springs provided by volcanic activity are used for heating, bathing, and tourism. The same geological activity that could be seen as purely dangerous is instead integrated into the economy and daily life. The volcanic soils of Iceland are incredibly fertile, supporting agriculture that would be impossible in less volcanic regions. People don't flee from volcanoes. They stay because the benefits often outweigh the risks, and the risks themselves are manageable through knowledge and preparation. Consider the productivity of volcanic soils throughout history. In Indonesia, around Mount Merapi, despite the volcano's considerable danger, people have continuously returned to farm the rich volcanic soils. In the Philippines, communities thrive on islands shaped by volcanic activity. In New Zealand, thermal areas provide resources and beauty. In Hawaii, volcanic landscapes have shaped an entire culture. The soil enriched by volcanic minerals supports crops that can't grow elsewhere. The geothermal resources heat homes and power towns. The volcanic landscapes attract visitors and create economic opportunities. Yes, volcanic eruptions can be destructive, but the volcanic landscape itself is generative. It creates the conditions for abundance. It enriches the soil. It provides heat. It shapes the terrain in ways that are often beautiful, creating mountains, valleys, and features that define regions. This is why, across human history, people have always been drawn to volcanic regions, despite the risks. The combination of danger and abundance creates a particular kind of vibrancy that exists nowhere else. People accept the risk because they understand it's temporary. Eruptions happen periodically. Between eruptions, sometimes decades or centuries of peace. During those periods, the land is incredibly productive. This cycle of eruption and dormancy, danger and abundance, has shaped human civilization in countless regions. Modern volcanology has become increasingly sophisticated in predicting not just when eruptions will occur, but what type of eruption will happen. The composition of magma determines behavior. Thick, viscous magma tends to produce explosive eruptions. Thin, low-viscosity magma tends to produce flowing eruptions. Scientists can determine magma composition by analyzing gas emissions and other volcanic signals. They can predict whether an impending eruption will send ash high into the atmosphere or whether lava will flow gently down slopes. This predictability extends to the hazards posed. An explosive eruption poses different risks than a flowing eruption. Communities can prepare specifically for the type of danger their volcano is most likely to produce. Networks of monitoring stations surround active volcanoes. Real-time data is transmitted to research centers. Scientists analyze patterns, looking for precursors. The entire system is designed to provide maximum advance warning so that people can move to safety before danger strikes. The history of volcanic eruptions teaches us patterns and cycles. Some volcanoes erupt regularly, almost on schedule. Mount Stromboli in Italy has been erupting continuously for thousands of years, sometimes almost daily, releasing pressure constantly rather than building stress toward a catastrophic eruption. This continuous release of energy is actually a sign of a healthy system, one that isn't accumulating dangerous pressure. Other volcanoes go dormant for decades, sometimes centuries, and then erupt again. But dormancy doesn't mean unpredictability. Scientists studying the geological record can estimate how long dormant periods typically last for any particular volcano. A volcano that last erupted 50 years ago might typically sleep for 100 years. That knowledge provides comfort to people living nearby. A major eruption is not imminent. The stress has been released. The next period of heightened risk is decades away. This cyclical behavior, while powerful, is also orderly. It's comprehensible. It's something you can prepare for and live with, just as humans have done for millennia. What transforms volcanic risk from purely fearful to manageable is this combination of understanding, monitoring, and preparation. We don't control volcanoes. We never will. They're too powerful, too fundamental to planetary processes. But we've moved beyond ignorance. We understand them now. We can see them coming. We can prepare for them. We can build communities and infrastructure designed to withstand volcanic hazards. We can evacuate people to safety before eruptions occur. We can use volcanic resources productively during the long periods of dormancy. We've learned to live with volcanoes, not despite them, but alongside them, understanding them as permanent features of our landscape that we can adapt to and work with. This is the peace that comes from knowledge. Volcanic landscapes shaped by eruptions and dormancy, danger and productivity have been home to human civilizations for thousands of years. People return to them again and again because the abundance outweighs the risk, and the risk itself becomes manageable once you understand it. Volcanoes are no longer mysteries. They're features we can study, predict, and prepare for. They're part of a living, dynamic planet that maintains its own thermal balance through the release of internal heat. And that balance, that cycling of energy from deep within the Earth to the surface, is something to appreciate rather than fear. Tsunamis are different from what came before. They arrive with less warning than earthquakes, less warning than volcanic eruptions, and often with more sudden violence than either. A tsunami is fundamentally a displacement of water, a wave or series of waves generated by a sudden movement of the ocean floor, a rapid vertical shift that pushes or pulls an enormous volume of water. In most cases, that movement comes from an earthquake in a subduction zone, where one tectonic plate slides beneath another, a process that happens with dramatic suddenness when the stress accumulated over decades or centuries finally exceeds the friction holding the plates in place. The friction between the plates builds stress slowly, millimeters per year of motion, prevented by friction until the force becomes overwhelming. The stress releases suddenly in a moment. The plates slip. The ground moves. If that movement happens beneath the ocean, the water directly above the epicenter is displaced suddenly, pushed down, or lifted up depending on the direction of plate movement, the direction of the fault rupture, the angle of the subducting slab. That displacement propagates outward in waves that travel across entire oceans at incredible speeds, carrying the energy released from the earthquake distributed through water that extends from the surface to the ocean floor. In deep water, tsunami waves can travel at nearly 900 kilometers per hour, moving as fast as a jet aircraft, driven by the energy released from the earthquake, the enormous amount of kinetic energy that comes from moving massive plates. The waves are fast because they travel through the entire water column, from surface to sea floor, and the deep water allows them to move unimpeded by friction from the bottom. As the waves approach shore, where the water gets shallower, their speed decreases, but their height increases, a consequence of fluid dynamics and energy conservation. Deep water tsunami waves might be only a meter tall, barely noticeable to ships out at sea passing overhead. The wavelength measured in hundreds of kilometers, the wave period measured in minutes. But as that same wave reaches the continental shelf and the water becomes shallow, the wave can't move as fast. The speed drops to 20 or 50 kilometers per hour, but the height increases dramatically as all the energy that was spread through deep water becomes concentrated in much shallower water. Waves that were invisible in deep water suddenly become 10, 20, or 30 meters tall as they reach the coast, sometimes even taller depending on the earthquake's magnitude and the continental shelf's shape. The energy concentrated in these massive walls of water can reshape entire coastlines, moving sand, carrying away buildings, crossing kilometers inland depending on the slope of the shore. The 2004 Indian Ocean tsunami stands as one of the most significant natural disasters in recorded history. But it also teaches us how the system works, how geological processes translate into consequences, how understanding those processes allows us to prepare. A magnitude 9.1 earthquake near Sumatra on December 26, 2004, triggered one of the deadliest tsunamis ever recorded, but it also created the catalyst for building the warning systems that have since saved countless lives. The earthquake occurred in a subduction zone where the Indo-Australian plate is being forced beneath the Eurasian plate, a process that creates enormous stress as the denser plate is driven downward into the hotter mantle. Stress had been building in this zone for centuries, perhaps for millennia, accumulating seals entirely beneath the ocean floor, the two plates grinding against each other, friction holding them in place even as deeper forces kept pushing them together. When the stress exceeded what the rock could support, the plates slipped. The rupture started at the hypocenter, the point where stress was greatest, and propagated along the fault for several minutes. A rare slow-motion earthquake in terms of rupture speed, the fault breaking from north to south along hundreds of kilometers of the subduction zone. The Indo-Australian plate dropped several meters below the Eurasian plate in a sudden movement, one of the largest vertical displacements ever recorded in an earthquake. The ocean floor above this boundary lurched upward and downward, creating a bulge that pushed water upward. An enormous volume of water was displaced, perhaps several billion cubic meters depending on how you measure it, enough water to fill thousands of large reservoirs. The water that had been sitting peacefully above the epicenter suddenly found itself without support beneath it. Gravity pulled it down, but water from surrounding areas rushed in, creating waves that propagated outward in all directions. A series of waves moving away from the epicenter at hundreds of kilometers per hour. These waves traveled across the entire Indian Ocean, reaching coasts thousands of kilometers away within hours, hitting East Africa on the western side of the ocean, roughly 7 hours after the earthquake occurred, hitting Thailand and Indonesia much sooner because they were closer. In some places, the waves were so tall, the completely inundated coastal areas, reaching heights of 30 meters or more in some locations, completely overwhelming any natural or human-made barriers. Beaches became inland, turned into open water. Entire towns were swept away, buildings flattened by the force of the water and the debris it carried. The waves killed approximately 230,000 people across multiple countries, from Indonesia closest to the epicenter, to Thailand, Sri Lanka, India, East Africa. The devastation was profound and widely felt, transforming entire regions, displacing millions of people, causing economic damage in the billions of dollars. But what emerged from this catastrophe was understanding and commitment. Scientists studying the 2004 tsunami learned more about tsunami generation, tsunami propagation, and tsunami impacts than from any previous event. Instruments recorded the earthquakes. Buoys in the ocean measured the passing waves. Surveying teams documented how far inland water penetrated, how high waves reached, how much damage resulted from the waves versus other causes. The data was enormous and detailed. The international response to the disaster was one of unprecedented coordination and generosity. Nations that had no direct connection to the affected areas sent rescue workers, supplies, medical assistance. This was disaster convergence, the reliable phenomenon where disasters bring out human compassion and cooperation on a massive scale, where people who have never met work together to help strangers, where national boundaries become irrelevant in the face of human suffering. The 2004 tsunami also sparked the development of sophisticated tsunami warning systems that have fundamentally changed how the world responds to tsunami hazards. Before that disaster, the Indian Ocean had no coordinated early warning system, no integrated network of seismic monitoring stations and ocean sensors and communication protocols working together to alert coastal communities. After the 2004 disaster, understanding grew about what was needed, what had been lacking, what could prevent another catastrophe on that scale. Systems were developed and deployed around the Indian Ocean and throughout the Pacific, each region building warning capabilities appropriate to its particular needs and resources. Modern tsunami warning systems work through a combination of seismic monitoring and OCE and sensors, a two-pronged approach that provides both fast detection and subsequent verification. When an earthquake occurs beneath the ocean, seismic networks positioned on land and on islands detect it within minutes, sometimes just a minute or two, the seismic waves traveling rapidly through the rock and being detected by sensitive instruments buried in the ground or placed on bedrock. Computers calculate the earthquake's location by analyzing the time differences between when P waves and S waves arrive at different stations. They calculate the depth by analyzing wave amplitudes and patterns. They calculate the magnitude by analyzing the size and frequency characteristics of the waves. The entire process happens within minutes. If the earthquake is large enough and occurs in a region where it's likely to generate a tsunami, a warning is issued immediately to all coastal areas in the path of potential tsunami waves. Coastal areas that could be affected by tsunami waves receive alerts telling them to move to higher ground, to leave beaches and low-lying areas, to move away from harbors and bays where tsunami waves might be funneled and amplified. The alert travels through multiple channels: television, radio, cell phone systems, sirens in some places, ensuring that the message reaches as many people as possible. Additionally, networks of sensors called buoys are positioned in the open ocean at strategic locations where they can detect passing tsunami waves, positioned along shipping lanes and in likely tsunami paths. These buoys have sensors that can detect passing tsunami waves, instruments that measure water pressure, instruments that measure sea level changes. When a tsunami passes beneath a buoy, the water level rises and falls as the wave passes, and the sensors detect that slight but measurable change in water pressure. This information is transmitted via satellite to warning centers, where it's received in real time, providing confirmation that a tsunami is actually traveling across the ocean. Scientists receive this real-time data about tsunami characteristics, can calculate the tsunami's actual height and wavelength and speed based on buoy measurements rather than just estimates based on earthquake parameters. This allows them to issue more detailed warnings about expected wave heights and arrival times in different locations, refining the alert to be more specific about which communities will experience larger waves and when those waves will arrive. This system works. Since the development of Indian Ocean and Pacific tsunami warning systems, early warnings have saved countless lives. The 2011 Japan tsunami occurred with warning systems in place, and people evacuated, and deaths were prevented. The 2015 Chile tsunami was detected, and warnings were issued, and people moved to safety. Communities have been spared the complete devastation that might otherwise have struck because they had advance warning and knew what to do with it. The technology works, the science works, the system works because it's built on understanding how earthquakes generate tsunamis and how those tsunamis travel. Understanding that allows us to provide early warning and save lives. What makes tsunami warning possible is the speed at which seismic waves travel through the earth compared to the speed at which tsunami waves travel through water, a fundamental difference in physics that provides us with a critical window of opportunity. Seismic waves from an earthquake travel through the solid rock of the earth at speeds of 5 to 14 kilometers per second depending on the type of wave. P waves traveling fastest at around 13 kilometers per second. S waves traveling slower at around 7 kilometers per second, both moving through rock at velocities that depend on the rock's density and elasticity. Tsunami waves traveling through water move at hundreds of kilometers per hour, which sounds fast until you realize it's only about 250 meters per second in deep water, much slower than seismic waves that are moving at thousands of meters per second. This means seismic detectors positioned on shore or on islands feel the earthquake and transmit warnings before tsunami waves arrive at distant shores, a difference of minutes to hours depending on distance. The warning time might be just minutes in nearby areas if you're close to where the earthquake occurred. The tsunami waves are right behind the seismic waves, but for coasts thousands of kilometers away, the warning time can be substantial. A tsunami heading toward the east coast of Africa might have 10 hours to travel across the Indian Ocean, giving early warning systems that whole period to detect the earthquake, assess whether it will generate a tsunami, and issue warnings to coastal areas. A tsunami heading toward Australia might have 8 hours. A tsunami heading toward Thailand might have less than an hour. This window, this interval between when the earthquake occurs and when the waves arrive, is the crucial period during which people can move to safety. You don't need much time. Moving uphill a few hundred meters or several stories up a building is usually enough to escape tsunami waves, moving away from the immediate shoreline or up to higher elevations. Moving inland, even just 1 or 2 kilometers, significantly reduces risk. Communities in tsunami-prone areas practice these evacuations regularly. They conduct drills where they actually practice the routes. They identify safe zones that are high enough or far enough inland to be safe. People know where to go. They know how to get there quickly, having practiced the routes and timed themselves. They know what to do when a tsunami warning is issued. There are emergency plans in place that have been developed based on tsunami hazard assessments for their specific communities. That preparedness, that practice response, is the difference between a disaster that kills thousands and one that takes fewer lives. Between an evacuation that happens in panic with people not knowing where to go, and one that happens in organized fashion, with people knowing exactly what to do because they've practiced it. The Krakatoa eruption of 1883 demonstrates a different way tsunamis are generated. While most tsunamis come from earthquakes, they can also be created by volcanic eruptions. The Krakatoa eruption was so violent, so energetic, that the explosion itself displaced an enormous volume of water. The tsunami generated by this eruption reached heights of 135 feet in some places. It destroyed coastal towns and villages along the Sunda Strait between Java and Sumatra, killing approximately 36,417 people. Many of these deaths came not from the volcano directly, but from the tsunami waves it generated. The explosion was heard from hundreds of kilometers away, one of the loudest sounds ever recorded. The volcanic ash circled the entire Earth within weeks, so much material thrown into the atmosphere that it reduced the amount of solar radiation reaching the ground, actually cooling global temperatures for months afterward. This eruption was catastrophic by any measure. But it also provided data that improved our understanding of how volcanic eruptions generate tsunamis. Scientists studying the Krakatoa event and other volcanic tsunamis learned that the mechanism is similar to earthquakes in some respects. A sudden displacement of water, whether from an earthquake or a volcanic explosion, creates waves that propagate outward. The energy in those waves depends on the amount of water displaced and the speed of the displacement. Larger displacements and faster movements create larger waves. What's reassuring about understanding tsunami generation is recognizing that while they're powerful, they're not random. They don't appear from nowhere without any geological context. They're created by earthquakes in subduction zones, by volcanic eruptions, by submarine landslides. These are all geological phenomena that occur in identifiable locations. Subduction zones are mapped. We know where they are around the world. Volcanoes are monitored. We know which ones are active. We understand the processes that generate tsunamis. We can map the coastlines that are at risk from particular earthquakes. We can estimate tsunami heights based on earthquake magnitude and location. We can model how tsunami waves propagate across oceans. All of this understanding allows us to prepare. Communities at risk from tsunamis have warning systems in place. They have evacuation plans. They have trained responders. The warning time might be measured in minutes for nearby areas, but it's usually enough. And for distant coasts, the warning time can be hours, providing ample opportunity for complete evacuation. The fact that the 2004 tsunami occurred before modern warning systems were in place is tragic, but it also drove the development of those systems. The tragedy was not inevitable. It occurred because the warning infrastructure didn't exist yet. Once the systems were built and deployed, they began saving lives immediately. In 2011, a magnitude 9.0 earthquake off the coast of Japan generated another major tsunami. But this time, warning systems functioned. People received alerts and evacuated to higher ground before the waves arrived. The earthquake and tsunami caused significant damage, but the early warning system prevented the scale of death that might otherwise have occurred. In the years since, the systems have been improved, expanded, refined, and deployed to new regions. Tsunami warning networks now exist in multiple oceans. Scientists work continuously to improve the systems, to make warnings more accurate, to reduce the time between detection and alert. This is human ingenuity responding to natural disaster. We don't control the earthquakes or volcanoes, but we've created systems that allow us to detect their effects quickly enough to save lives. The system works because we understand the physics involved. Seismic waves travel faster than tsunami waves. That's a fundamental fact of physics that can't be changed. But it's a fact we can exploit using seismic detection to provide advance warning before tsunami waves arrive. We've built networks of sensors and communication systems that function continuously, We've trained people to respond to warnings. We've educated communities about what to do when a tsunami warning is issued. All of this comes from understanding how tsunamis work, where they're likely to occur, and how to detect them quickly. Tsunami patterns also teach us about long-term safety and risk assessment, revealing patterns of natural hazards that have repeated throughout recorded history and into prehistoric times. While large tsunamis can be devastating, they're also relatively infrequent in any particular location when you consider geological timescales. The 2004 Indian Ocean tsunami was unusual in its magnitude and in the scale of its impact across multiple countries. Such giant tsunamis occur in the Indian Ocean maybe once every several hundred years or longer, sometimes with even longer intervals between events of that magnitude. The 1883 Krakatoa tsunami was similarly rare, a once-per-several-centuries scale event that surprised people who thought such disasters were even rarer. Most coastal areas where earthquakes can generate tsunamis experience large tsunami-generating earthquakes maybe once every 100 to several hundred years on average, though the actual timing is random and doesn't follow regular schedules. This means that while the risk exists, the probability of experiencing a large tsunami in any given year is quite small for most coastal locations, far less than 1% in many places, maybe 0.5% annually for a location that averages a major tsunami every 200 years. Knowledge of historical tsunami patterns allows scientists to estimate how frequently large tsunamis are likely to strike any particular coast by studying geological records of past tsunamis, by looking at coral cores and sediment layers that show tsunami deposits, by analyzing historical records and eyewitness accounts of past events. A coastline with a record of major tsunamis every 200 years or so is at higher risk than a coastline where large tsunamis occur only once every 1,000 years. And this risk information shapes how communities prepare. Communities can use this information to inform their preparation and planning, to decide how much to invest in warning systems and evacuation infrastructure. Risk varies geographically, and understanding those variations helps communities prepare appropriately for their specific location, spending resources where they're most needed, preparing most intensively in areas of highest risk. Some coastlines face higher tsunami risk and might need more robust warning systems and more regular evacuation drills to ensure readiness. Others face lower risk and might need less intensive preparation while still maintaining basic warning infrastructure. But across all tsunami-prone regions, the principle is the same and fundamental to survival. Preparation and early warning save lives. They reduce deaths from tsunamis. They allow communities to function and recover faster from disasters. We understand the processes that generate tsunamis. We've built systems to detect them and warn communities. We've trained people to respond to warnings. When a major tsunami-generating earthquake occurs, the system activates almost immediately. Seismic networks detect the earthquake. Computers calculate its characteristics. Warnings are issued. Warnings spread through communities via multiple channels. People move to higher ground. The waves arrive and pass. Most people in coastal areas survive because they've moved to safety, because the preparation and warning system worked. The system works because it's based on understanding how nature actually works, understanding the physics of earthquakes and water waves, and how energy propagates through the earth and oceans, not on hoping we can prevent natural events or somehow stop the ocean from moving. What makes tsunamis genuinely relaxing to contemplate in the context of understanding how natural disasters work is recognizing that they're not random acts of destruction appearing from nowhere, not chaotic forces immune to comprehension. They're consequences of geology, of processes we can study and understand and predict. Earthquakes in subduction zones, by their nature, sometimes generate tsunamis. Earthquakes large enough and at the right depth and with the right kind of motion to displace water and create waves. Volcanic eruptions that affect ocean water generate waves when the volcano explodes or collapses and displaces huge volumes of water. These processes are predictable in their locations. We know where subduction zones are. We've mapped them thoroughly around the world. We can identify which ones are most active and most dangerous. We know which regions are at higher risk of experiencing tsunami-generating earthquakes. We can monitor the volcanoes that could potentially generate tsunamis. Watch them for signs of activity that might lead to eruption. We can detect earthquakes within minutes, sometimes faster, using seismic networks that cover the globe. We can track tsunami waves as they travel across oceans using buoy networks and satellite data. We can issue warnings before waves reach distant shores, giving people time to move to safety. We can't stop the earthquakes or tsunamis from occurring. We don't need to. We just need to move people out of the way, and we've become quite good at that. Our warning systems and evacuation procedures are effective and save lives. The speed of seismic waves gives us warning time that we didn't have before warning systems were developed. Modern technology lets us distribute that warning globally almost instantly, a message traveling at the speed of light from warning centers to coastal communities. Communities practice their response so people know exactly what to do when a warning arrives. They've drilled the evacuation routes. They've practiced the moves. They know where to go and how fast they need to move. The system is not perfect. In rare cases, warnings might be delayed due to technical issues. Evacuation routes might be blocked by damage from the earthquake itself. Communication might fail in areas with limited infrastructure. But the system works in the vast majority of cases, the vast majority of times people receive warnings and evacuate successfully, and lives are saved. Lives that would have been lost without warning systems are saved through them. Thousands of lives in multiple countries since these systems were deployed. This is a triumph of human ingenuity and understanding applied to natural processes we cannot control. We've learned to live with tsunamis not by preventing them, which we can't do, but by preparing for them, by understanding them at a level that allows us to anticipate them and respond effectively, and by using that understanding to protect ourselves and each other when they occur. Atmospheric systems work differently than geological ones, but they follow the same principle that brings peace to understanding natural disasters. Where earthquakes release stress suddenly and tsunamis propagate outward from a single point, hurricanes and typhoons are distributed phenomena, enormous rotating systems that form over warm ocean water and carry their energy across thousands of kilometers. They're not random. They don't appear from nowhere. They follow patterns that are so predictable that meteorologists can track them days in advance, watching their formation, predicting their paths, calculating their intensity with remarkable accuracy. The mechanics of hurricane formation are actually deeply reassuring once you understand them, because the process is orderly, follows physical laws that never change, and creates patterns that repeat year after year, season after season. Understanding these patterns doesn't eliminate the power of hurricanes or the damage they can cause, but it transforms them from mysterious phenomena into comprehensible events, from random threats into predictable occurrences that communities can prepare for and respond to with confidence. Hurricanes form over warm ocean water, specifically over tropical and subtropical waters, where sea surface temperatures exceed approximately 26.5 degrees Celsius. This temperature threshold is not arbitrary. It's the point at which warm water has enough energy to fuel atmospheric convection, the process where warm air rises and cooler air sinks in continuous cycles. As air rises over warm water, it carries moisture with it, moisture that condenses into clouds as the rising air cools with altitude. That condensation releases latent heat, energy that was stored in the water vapor, energy that further accelerates the rising motion of air. The process feeds itself, creating a positive feedback loop, where warming drives more convection, which drives more heat release, which drives more convection. This self-sustaining process is actually elegant, a demonstration of how a system can reach remarkable organization and strength once certain conditions align. Wind shear, the change in wind speed and direction with altitude must be low for this process to organize into a rotating system. When wind shear is high, the rising column of air gets sheared apart, torn into separate pieces, preventing the organization of a coherent storm. But when wind shear is low and other conditions align, the rising air column begins to rotate. The Coriolis effect deflecting moving air rightward in the northern hemisphere and leftward in the southern hemisphere, creating circulation around a central low-pressure area. The physics here is consistent and reliable. These same mechanisms have been operating for millions of years, creating organized rotating storms on Earth whenever conditions favored them. As the rotation tightens, wind speeds increase, drawing in more air, more moisture, more energy. The system reorganizes into the distinctive spiral shape visible from satellite, the classic hurricane structure with outer bands of thunderstorms extending outward, an intermediate eye wall where the strongest winds occur, and at the absolute center, the eye itself, a region of relative calm where pressure is lowest and winds are light. This structure is so consistent that meteorologists can identify it instantly, can measure its intensity from satellite imagery, can predict how the storm will evolve based on the structure they observe. What's remarkable about hurricane formation is how predictable it is once the conditions are right. Meteorologists don't predict whether a hurricane will form in a given season. They predict how many will form. They can estimate with considerable accuracy how many major hurricanes will occur in any given Atlantic or Pacific season, based on ocean temperatures, atmospheric circulation patterns, and wind shear forecasts months in advance. This seasonal forecasting is itself a form of comfort, a way of knowing what to generally expect throughout a year. The formation of individual storms follows similar patterns. When a disturbance like a tropical wave or area of low pressure moves over warm water with favorable atmospheric conditions, meteorologists can watch it organize in real time, seeing the rotation begin, the pressure drop, the wind speeds increase, the classic structure emerge. There is something genuinely reassuring about watching a system develop predictably, about seeing each stage of organization unfold exactly as the physics suggests it should. The path that a hurricane takes is also predictable, determined by the steering currents of the broader atmospheric circulation. High-pressure systems deflect hurricanes, steering them toward lower pressure, following the same laws of motion that guide everything moving in a fluid. The position of the jet stream, the boundary between tropical and polar air masses, influences how quickly storms move and in what direction. Meteorologists track these steering influences and predict hurricane paths with increasing accuracy, producing track forecasts that show the most likely path a storm will follow. Modern hurricane track forecasts are often accurate enough to narrow down which coastline a hurricane will strike a week in advance. The uncertainty in these forecasts decreases as a hurricane approaches, because the closer an event is, the better we can observe the current conditions and determine what will happen next. This improving forecast accuracy is a triumph of meteorological science, a direct result of better satellites, better computer models, better understanding of atmospheric physics. Intensity prediction is more challenging than track prediction, but it's also becoming increasingly accurate as meteorologists better understand the factors that control how rapidly hurricanes strengthen or weaken. The intensity of a hurricane depends on how much warm water the storm is moving over, how much moisture is available in the lower atmosphere, what the wind shear is like, and various other factors that meteorologists measure and plug into forecast models. A hurricane moving over cooler water will weaken because it's losing its primary energy source, the warm water that fuels convection. A hurricane moving over progressively warmer water can intensify or maintain its strength, sometimes even strengthening dramatically if conditions are ideal. Understanding these relationships allows meteorologists to provide intensity forecasts, showing what strength a hurricane will likely reach as it approaches land. This information allows coastal communities to prepare specifically for the hurricane they're going to experience, not just some generic hurricane, but the actual forecast intensity and path. A community facing a forecast Category 4 hurricane can prepare for extreme winds, severe storm surge, and catastrophic damage. A community in the path of a forecast Category 1 hurricane can prepare more moderately, knowing that while damage will occur, it's likely to be less severe. This specificity in forecasting transforms the preparation process from general worry to targeted action, from anxiety about unknown threats to concrete planning for known challenges. The infrastructure for hurricane prediction and warning is extensive and global. Satellites constantly observe the ocean and atmosphere, looking for developing disturbances. Meteorological agencies in hurricane-prone regions operate sophisticated radar systems that can detect intense rainfall and wind patterns within storms. Aircraft equipped with specialized instruments fly into hurricanes, dropping sensors that measure the storm's structure and intensity. Buoys in the ocean measure sea surface temperature and other ocean conditions. This constant observation creates a detailed picture of where hurricanes are, how strong they are, where they're going, and how strong they're likely to become. Warnings are issued to coastal communities well in advance of hurricane arrival, providing days of notice so people can prepare, evacuate if necessary, secure property, gather supplies. The warning system has phases, tropical storm watches and warnings before a storm becomes a hurricane. Hurricane watches issued 48 hours before expected arrival. Hurricane warnings issued 36 hours before expected arrival in some regions. These successive warnings give people multiple opportunities to respond, to move if they haven't already moved, to take final preparations. What brings peace to living in hurricane-prone regions is recognizing that hurricanes are not random or mysterious. They follow patterns. They form under specific conditions. They move along predictable paths. Their intensity can be estimated. Their impacts can be anticipated. Communities can prepare for specific threats rather than vague possibilities. Evacuations can be ordered with specific information about what's coming, allowing people to leave with confidence that the preparation is proportional to the actual threat. This is different from a world where hurricanes appeared suddenly with no warning, where people didn't know which areas would be hit or how strong the storm would be. In that hypothetical world, hurricane risk would be far more anxiety-inducing. But in the actual world, where meteorology has advanced to the point where hurricanes are tracked from their earliest formation and their behavior is predicted accurately, hurricane risk becomes manageable through preparation and early action. Understanding hurricanes as organized systems also makes their ecological role apparent. Hurricanes transport enormous amounts of moisture across regions, releasing precipitation as rainfall. In areas with limited rainfall, hurricanes can be the primary source of water for the year. The heavy rainfall from hurricanes replenishes groundwater, fills reservoirs, provides water for agriculture and human consumption. Yes, the intense rainfall can cause flooding, but in dry regions or during dry seasons, that rainfall is essentially a water delivery system, a giant water transport that moves moisture from the tropical oceans where it evaporates to land regions where it's needed. The ocean benefits from hurricane passage as well. The intense winds of a hurricane churn up the ocean surface, bringing cold, deep water to the surface, mixing the water column. This mixing redistributes nutrients that have accumulated in the deep water, bringing them back to the surface where they're available to phytoplankton. The productivity of ocean ecosystems increases after hurricane passage due to this nutrient enrichment. Fish populations benefit from the increased food supply. The complex food webs that support commercial fisheries depend on this hurricane-driven mixing and nutrient redistribution. Without hurricanes, ocean productivity in many regions would be lower, fisheries would be less productive, and food security would suffer. Coastal ecosystems evolved in the presence of hurricanes, shaped by them, dependent on them in various ways. Mangrove forests, salt marshes, and other coastal wetlands are adapted to hurricane disturbance. The strong winds and storm surge can damage these ecosystems temporarily, but they're designed to recover. Many coastal plants have flexible structures that bend rather than break, allowing them to survive hurricane-force winds. The salt marshes can quickly recover after storm surge pushes salt water inland. Mangrove seedlings establish in disturbed areas where the forest canopy was opened by the hurricane. The disturbance actually maintains diversity in these ecosystems by preventing any single species from dominating, by opening space for multiple species to establish. Without periodic hurricane disturbance, coastal ecosystems would become less diverse, would be dominated by species that were most competitive in stable conditions, would lose some of the biodiversity that exists because, the disturbance cycle. This is another aspect of the piece that comes from understanding hurricanes. They're not purely destructive forces imposed on ecosystems. They're part of the natural system, part of the mechanism that maintains coastal ecosystems, part of the disturbance regime that coastal species have adapted to. Life on coasts in hurricane regions is shaped by the expectation that powerful storms will come periodically, and the ecosystems have evolved to handle that, to recover from it, to even depend on it for long-term health. The seasonal pattern of hurricane activity is also reassuring, a rhythm that allows communities to prepare mentally and practically for the threat. In the Atlantic Basin, hurricane season runs from June through November, with peak activity in September and October. This predictability allows people to know when they should be most vigilant, when they should review emergency plans, when they should ensure that supplies are in place. Communities in hurricane regions don't live in constant fear of hurricanes. They live with an understanding that there's a season when the risk is elevated, a season when storms are possible, and outside of that season, the risk is extremely low. The rhythm of hurricane season creates a cycle that's comprehensible and plannable. Outside of season, people can relax, knowing that the atmospheric conditions are unfavorable for hurricane formation. During season, they're alert, but they know when to expect the threat, where to expect it based on historical patterns, and they prepare accordingly. What develops over time in communities living with hurricane risk is a kind of competence, a collection of knowledge and practices that become routine. People know how to secure their property before a hurricane. They know where to buy supplies. They know which routes to use for evacuation. They know how their insurance works. They know where emergency shelters are located. They know how their utility systems function and what to expect after a storm. This knowledge, accumulated through experience and passed from one generation to the next, makes living with hurricane risk manageable. New residents arriving in hurricane regions quickly learn these practices from long-term residents. Schools teach hurricane preparedness, businesses plan for hurricanes, governments maintain infrastructure designed to withstand hurricanes. All of this creates a system where people are not helpless victims of nature, but informed participants in disaster preparedness and response. Tornadoes are fundamentally different from hurricanes, though they're often confused because both involve rotating air and both can produce destructive winds. Where hurricanes form over warm oceans and develop over days, tornadoes form over land during specific conditions that occur over hours, and they typically last for minutes, though sometimes lasting longer, occasionally even for an hour or more in extreme cases. Where hurricanes are enormous systems spanning hundreds of kilometers, tornadoes are relatively small, typically ranging from a few hundred meters to a few kilometers in width. Where hurricanes are tracked from their formation and provide days of warning, tornadoes can form with minimal warning, sometimes only minutes between when conditions become favorable and when a tornado develops. Yet tornadoes, like hurricanes, are not random phenomena that appear without warning. They form from specific atmospheric conditions that can be measured, predicted, and understood. Tornado formation requires wind shear, a change in wind speed and direction with altitude, and instability, a situation where air near the surface is much warmer than air aloft, creating buoyancy that drives upward motion. These are measurable quantities that meteorologists can detect in the atmosphere. When wind shear is oriented such that it creates rotation in the horizontal plane, and then updrafts in thunderstorms tilt this horizontal rotation into the vertical plane. A rotating column of air can form that descends from the cloud base toward the ground. When this rotating column reaches the surface, it's classified as a tornado, a vortex of wind moving at extreme speeds, the strongest tornadoes reaching speeds that exceed 480 kilometers per hour. The formation process, while producing extreme winds, is still governed by the same physical laws that govern all atmospheric motion. The damage from tornadoes is legendary because of these extreme wind speeds. Objects are picked up and moved, structures are reduced to rubble, vegetation is completely defoliated. The tornado's path is marked by complete devastation. Yet even this destruction, while severe, is localized, limited to the area where the tornado actually touches down, whereas hurricanes can produce destructive impacts across regions hundreds of kilometers across. What makes tornadoes particularly challenging compared to hurricanes is the short warning time. While hurricanes can be predicted days in advance, allowing for extensive preparation and evacuation, tornadoes typically have a warning lead time measured in minutes, sometimes only 10 to 15 minutes between when the National Weather Service issues a tornado warning and when the tornado reaches a community. This limitation is frustrating from a warning perspective, but it's not a reason for despair because shelter from tornadoes doesn't require going far. Unlike hurricanes, where the threat exists across an entire region and evacuation might mean traveling hundreds of kilometers, tornado shelter can be found right where you are. The warning time might be short, but it's actually long enough to move from an exposed location to protected shelter. Moving to a basement or interior room on the lowest floor of a building takes minutes. Moving away from windows and toward the center of the building where structure provides the most protection is quick and practical. Communities in tornado-prone regions understand this. They have tornado shelters in schools and public buildings. They understand where to go when a tornado warning is issued. They practice tornado drills regularly so that the motion to shelter becomes automatic, practiced, efficient. This preparedness allows survival even when the warning time is short. The protection provided by substantial buildings is remarkable. A concrete basement or interior room can protect occupants from winds that would be lethal outside, from flying debris that would be fatal without structure. The building itself, through its design, through its mass and strength, provides the protection that warning time cannot provide. Understanding that shelter from tornadoes is immediately available, that buildings provide effective protection, that communities practice the action of sheltering, all of this removes much of the psychological burden that short warning times might otherwise create. Understanding tornado seasonality, similar to hurricanes, provides some comfort. Tornadoes occur most frequently in spring and early summer in the central United States, when warm, moist air from the Gulf of Mexico collides with cold, dry air from Canada and the Rocky Mountains, creating the atmospheric instability and wind shear that tornadoes require. This seasonality is so pronounced that people living in Tornado Alley know that spring is the season of elevated risk. In spring, they monitor weather forecasts carefully. They're alert to weather watches and warnings. They're prepared to act quickly if a tornado warning is issued. Outside of spring, the risk decreases significantly. Tornadoes can occur at any time of year, but they're relatively rare outside of the peak season. This seasonal pattern again creates rhythm, a season of vigilance and a season of relative relaxation. Tornado detection technology has improved dramatically in recent decades. Doppler radar can detect rotation within thunderstorms before a tornado forms, allowing meteorologists to issue tornado watches when conditions are favorable and the atmosphere shows signs of rotation. When rotation tightens, wind speeds increase and radar signatures become very distinctive, tornado warnings are issued. Damage surveys after tornadoes provide information about tornado intensity and path, allowing meteorologists to improve their understanding of tornado behavior and improve warning systems. Storm chasers and researchers deploy instruments in tornado-prone areas to gather direct measurements of tornado dynamics. All of this observation and study improves understanding of how tornadoes form and how they behave, which improves forecasts and warnings. The relationship between tornado frequency and magnitude is similar to earthquakes. The most violent tornadoes are relatively rare. Very strong tornadoes, those capable of producing catastrophic damage, occur only occasionally. Moderate tornadoes, weak to strong, but not violent, are more common. This inverse relationship between frequency and magnitude means that locations with a history of frequent tornadoes are experiencing regular moderate storms that destroy individual buildings but don't level entire communities. Locations where strong tornadoes are rare experience very infrequent events, but when they do occur, they can be more intense. Communities can use historical records to estimate how often strong tornadoes are likely, to plan accordingly, to know whether they should expect a strong tornado roughly every century, every 5 decades, every few decades, depending on the location. This historical perspective again provides understanding and reduces the randomness that makes disasters psychologically difficult. Tornado preparedness has become increasingly sophisticated over the decades as communities have learned from experience, and research has advanced our understanding of what actually protects people during tornadoes. Safe rooms designed to withstand tornado force winds are installed in houses and buildings, based on engineering research that examined how buildings fail under tornado winds and what structural features provide the best protection. These rooms are often built around existing interior spaces like bathrooms or closets, reinforced with structural bracing, designed to protect occupants even if the building around them is destroyed. The walls are anchored to the foundation. The roof is reinforced. The structure is designed as a fail-safe, a bunker within the building that remains safe even if the building itself is compromised by extreme winds. Communities have tornado shelters in public buildings, schools, emergency management facilities, and sometimes in mobile home parks where residents are particularly vulnerable due to the light construction of mobile homes. Tornado drill procedures are well established, practiced regularly in schools and workplaces, so that when an actual tornado warning is issued, people know exactly where to go and what to do. They don't have to think or hesitate or panic. They simply execute the practiced procedure. Warning systems have multiple redundancy. Warnings are issued through television, radio, cell phone alerts, sirens in many communities, ensuring that people receive notification of tornado threats through multiple channels so that even if one system fails, others will get the message through. All of this infrastructure for tornado safety exists because of understanding of tornadoes, because of recognition that tornadoes will continue to occur in tornado-prone regions, and because of commitment to protecting people through preparation and warning. The result is that while tornadoes remain dangerous and cause deaths and injuries, the death toll from tornadoes has actually decreased over time as preparedness has improved. Understanding the atmospheric conditions that produce tornadoes also provides some reassurance about the limits of the hazard. Tornadoes require specific conditions that don't occur everywhere at all times. They require wind shear, a change in wind speed and direction with altitude. They require instability, warmer air near the surface with cooler air aloft, and they require the right orientation of these features so that the wind shear can be tilted into vertical rotation by the updrafts of thunderstorms. These are measurable quantities that meteorologists can detect in atmospheric soundings and satellite data, and when they don't exist, tornadoes cannot form no matter what else might be happening in the atmosphere. Many locations have a favorable season when tornadoes are possible. The spring and early summer, when the collision of tropical and polar air masses creates the instability and wind shear that tornadoes need, and an unfavorable season when they're essentially impossible because the atmospheric setup doesn't support tornado formation. Many locations have an unfavorable latitude where the atmospheric conditions necessary for tornadoes don't occur with sufficient frequency or intensity. The fact that tornadoes occur in predictable locations during predictable seasons means that communities can be targeted in their preparedness, that resources can be allocated proportionally to risk. Tornado-prone regions can invest in warning systems and shelters because they know the risk is real and concentrated in their area. Regions outside of tornado-prone areas can rely on less intensive protection because the risk is minimal, allowing them to allocate resources to other hazards or other needs. This targeted approach to hazard mitigation is far more efficient than trying to protect everywhere against everything. And it's possible only because we understand where and when tornadoes occur. The damage from tornadoes, while severe, is also localized in ways that have important consequences for recovery. A tornado might destroy an area only a few hundred meters wide and a few kilometers long, leaving surrounding areas relatively unaffected. This means that relief and recovery can be focused on the affected area. Resources can be mobilized from surrounding areas that were not impacted because the surrounding areas were spared damage. And rebuild can begin quickly because most of the surrounding infrastructure remained intact and functional. Compare this to a hurricane, which might impact an entire region across hundreds of kilometers, damaging countless communities simultaneously, requiring relief resources on a much larger scale, and straining the ability of regional authorities to respond everywhere at once. The localized nature of tornado damage means that recovery, while difficult for the affected communities, can often be accomplished relatively quickly compared to hurricane recovery. Within months or a few years, tornado-affected communities can be rebuilt, infrastructure can be restored, life can return to normal. The surrounding communities that were spared damage provide shelter, support, supplies and workforce for rebuilding, accelerating the recovery process. The psychological impact of tornado recovery is also noteworthy. Communities that experience tornadoes sometimes report that the experience brings them closer together, that the shared experience of disaster generates solidarity and mutual support that persists long after the physical recovery is complete. Neighbors who were strangers before the tornado often become friends afterward. Communities develop a sense of shared identity around surviving the disaster together. This is part of the broader pattern of human resilience in the face of natural disasters, the tendency of communities to come together, support one another, and emerge stronger from adversity. The tornado becomes part of the community's history, a story that is told and retold, a moment that defines the community's character and strength. Beyond the individual storms themselves, hurricanes and tornadoes fit into broader patterns of atmospheric circulation that are themselves understandable and predictable. Hurricanes move along paths determined by the trade winds and westerlies, the massive circulation patterns that move air around the planet. Wind patterns that have been moving tropical air toward the poles and polar air toward the equator since the atmosphere existed. Tornadoes form in regions where different air masses collide, where boundaries between tropical and polar air masses create the instability and wind shear necessary for tornado formation. These boundaries move seasonally, shifting north in spring and summer, shifting south in fall and winter, creating the seasonal pattern of tornado activity. Understanding how individual storms fit into these larger patterns, how they're not isolated phenomena, but rather manifestations of planetary scale circulation, provides a sense of order and connectedness. Hurricanes are part of how the planet redistributes heat from the tropics toward the poles, a necessary process for maintaining Earth's climate. Tornadoes are part of how the atmosphere removes the instability created when contrasting air masses collide, a mechanism for maintaining atmospheric equilibrium. Both are essential to how the atmosphere actually works. Understanding this transforms them from random destructive forces into necessary components of a functioning planetary system. The formation of individual tornadoes, while less predictable than individual hurricanes, still follows a comprehensible sequence. Wind shear in the atmosphere tilts wind-shifted air horizontally, creating spin. Updrafts in thunderstorms then tilt this horizontal spin to the vertical, concentrating it in a rotating column of air. This column tightens due to conservation of angular momentum, the same principle that causes a spinning ice skater to spin faster as they bring their arms inward. The column descends. Pressure drops inside the column due to the centrifugal effect, pushing air outward, and when the column reaches the ground, a tornado is born. The physics here is consistent and unchanging. These same processes have been happening on Earth since the atmosphere existed. The problem is not that tornadoes are incomprehensible, but rather that the precursors are more subtle than for hurricanes, harder to detect with available technology, harder to forecast at the precise location and timing where they'll occur. But technological improvements are reducing this uncertainty. Radar is detecting rotation earlier. Satellite data is improving the identification of favorable environments. Computer models are improving the simulation of tornado dynamics. The warning time for tornadoes has actually been increasing over the decades as technology has improved. Tornadoes that would have had no warning 50 years ago now have 15 or 20-minute warnings. That improvement will likely continue. Understanding both hurricanes and tornadoes as atmospheric systems with identifiable causes, predictable patterns, and detectable signatures removes much of the mystery and fear that would otherwise accompany them. We don't control these storms. We never will. They're too large, too energetic, too fundamental to how the atmosphere works. The wind speeds in strong hurricanes and violent tornadoes are beyond human capability to withstand through strength or will. We cannot prevent the storms from forming. We cannot make them dissipate. We cannot divert them away from land through any means at our disposal. But we've learned something far more valuable than control. We've learned to predict them, to warn about them, to prepare for them, and to recover from them. We've learned to live in regions where they occur, developing warning systems and building codes appropriate to the risks. We've learned to use the data from observing these storms to improve our understanding of atmospheric processes, to improve our ability to predict future storms, to keep improving our ability to protect ourselves and each other. The next strong hurricane that forms over a warm ocean will follow the same physical laws that drove the previous ones. Meteorologists will track its formation, predict its path, forecast its intensity, issue warnings to communities in its path. People will prepare, will evacuate if necessary, will shelter in place with protection against expected wind and rain. The hurricane will arrive, will pass, will leave damage in some areas, will deposit beneficial rainfall in others that sustains agriculture and replenishes groundwater. Recovery will begin, and over time, communities will rebuild, often stronger and more resilient than before. The next tornado that forms in spring will develop from the collision of air masses that produce thousands of tornado possibilities each spring, will form when atmospheric conditions align just right, will follow a path determined by the motion of the thunderstorm that spawned it. Meteorologists will issue a warning. Communities will move to shelter. The tornado will pass. Damage will be assessed. Recovery will begin, sustained by the mutual aid and community solidarity that disasters consistently bring out in people. The system works because we understand how these storms form, how they move, where they're likely to occur, what to expect from them. This understanding allows preparation, which saves lives, which allows recovery, which transforms disasters from random catastrophes into predictable events that communities can adapt to and survive. And in surviving, in preparing and responding and rebuilding, people discover resilience, competence, and the deep satisfaction that comes from facing powerful natural forces, not with fear or denial, but with understanding and action. Floods arrive with a different logic than rotating storms or erupting magma, where hurricanes spiral inward and tornadoes descend from clouds. Floods move outward, spreading across landscape, following the simplest path water can take. A heavy rainfall over a watershed, a rapid snowmelt, a dam failure, a storm surge pushed inland by hurricane winds. All of these can trigger flooding. And yet floods, despite their appearance of chaos and unpredictability, follow fundamental principles that make them comprehensible, that make them manageable, and that ultimately reveals their essential role in how the world actually functions. Like the disasters that preceded them in this journey, floods are part of how Earth works, part of how water cycles through the atmosphere and across the land, part of how ecosystems are built and maintained. Understanding this transforms floods from purely destructive events into natural processes with both destructive and constructive elements, depending on how we understand them and live in relation to them. Understanding floods begins with understanding that water moves downhill, always has, always will, following gravity with perfect consistency. Rain that falls on a hillside will flow downward, will collect in streams, will flow into rivers, and eventually will reach the sea. This journey is not instantaneous. It takes time. Water moves through soil at different rates depending on soil composition. It pools in depressions. It spreads across flat areas. It concentrates into channels where topography channels it. The amount of water flowing at any given point in a river is called discharge, and it varies based on how much water is being added from rainfall, snowmelt, or groundwater. For most of the year in most locations, rivers maintain a relatively steady discharge, water flowing at a rate that the channel can accommodate without overflowing. But when intense rainfall occurs, when snowmelt accelerates, when multiple sources of water converge at once, discharge can increase dramatically. The river reaches its bank full stage, the point where water is at the level of the banks. If discharge continues to increase beyond that point, water spills over the banks and the surrounding land becomes flooded. This is the basic mechanism of flooding, and while it sounds simple, it's actually the foundation for understanding why flooding occurs, where it does and when it's likely to happen. The topography determines where rivers flow. The climate determines how much water falls as rain or accumulates as snow. The soils determine how quickly that water flows downhill. Human development determines how much of the landscape can absorb water versus how much water runs off immediately into channels. All of these factors combine to create a flood regime for a particular region, a pattern of how often floods of different sizes are likely to occur. This pattern is measurable, recordable, and can be studied over decades and centuries to understand how often major floods occur in a particular location, whether there's something that happens roughly every 5 years, or every 50 years, or every 500 years. Floodplains are perhaps the most misunderstood landscapes on Earth. People see them as wastelands, undesirable areas that should be drained or developed. In reality, floodplains are among the most biologically productive landscapes on the planet. They exist because rivers periodically overflow their banks and spread water and sediment across the surrounding landscape. This isn't a malfunction. This is how the river is supposed to work. The sediment the river carries, the soil particles eroded from the landscape upstream, gets deposited in the floodplain when the water spreads out and slows down. This deposition builds and maintains the floodplain, constantly renewing the soil. The water brings nutrients, organic matter, and minerals that fertilize floodplain vegetation. The periodic inundation prevents woody plants from growing too densely, maintaining open meadows and grasslands. The alternation between flood and drought creates diverse habitats that support an extraordinary diversity of plants and animals. Fish spawn in floodplain pools. Birds nest in riparian vegetation. Mammals find forage in floodplain meadows. The productivity of floodplain ecosystems is remarkable, often exceeding that of any other landscape type, supporting more biomass and more diversity per unit area than surrounding upland areas. Agriculture thrived on floodplains for millennia, precisely because the annual floods brought fertility, because the flooded soils were renewed each year by sediment and nutrients from upstream. Ancient Egypt's civilization was built on the annual floods of the Nile, which brought sediment from the highlands downstream, where it maintained the fertility of the delta and lower valley. The entire food security of a civilization of millions of people depended on understanding and working with the natural flood regime rather than attempting to prevent it. People understood that floods were beneficial, necessary, and predictable enough to plan around. The floods came at roughly the same time each year, brought roughly the same amount of water, and allowed agriculture to flourish in what would otherwise be arid landscape. The relationship between flood and fertility was direct and obvious, and the relationship between flood timing and agricultural productivity was so well understood that ancient peoples coordinated their entire civilization around the rhythm of the river. When the floods began to be controlled through dams and levees in the 1800s and 1900s, the sediment that had been flowing downstream stopped flowing. It accumulated behind dams instead. The floodplain downstream began to erode and lose fertility. The system that had sustained civilization for thousands of years was disrupted by the attempt to prevent flooding. The lesson here is that floods are not aberrations. They're the normal way that floodplain ecosystems function. Rivers without floods become ecologically impoverished. Floodplains without floods gradually degrade. The relationship between flood and ecosystem health is fundamental, and any attempt to completely eliminate floods creates new problems even as it solves the problems that motivated flood control in the first place. The seasonality of flooding is another reassuring aspect once you understand it. Similar to how hurricane season and tornado season provide rhythm and predictability to other atmospheric hazards. In many regions, floods are predictable, arriving at roughly the same time each year with remarkable consistency. In tropical regions with distinct rainy seasons, heavy rainfall and flooding are expected during the season when moisture-laden winds bring precipitation, allowing preparation months in advance. In temperate regions with winter snowpack, spring flooding comes as the snow melts in response to warming temperatures, a process that can be monitored and predicted based on snowpack measurements taken in the mountains. In regions with monsoons, the annual monsoon brings intense rainfall and predictable flooding, a cycle that has been understood and incorporated into human societies for thousands of years. This seasonality allows communities to prepare for floods, to know when they're likely to occur, to plan their activities and infrastructure around the expected flood timing. This predictability is itself comforting, a manifestation of order in natural systems. Farmers in floodplain regions understand the flood schedule. They plant crops that can tolerate flooding or in areas that won't flood at the expected time. They build structures above the expected flood level. They maintain cattle and other livestock in a way that accounts for periodic flooding. Indigenous peoples who lived on floodplains for millennia developed sophisticated understanding of flood timing and magnitude. They built settlements above the expected flood level. They harvested resources when flooding made them available. They organized their lives around the rhythm of the flood. This knowledge, accumulated over generations, represented a form of flood prediction and preparation that was amazingly effective. Modern hydrologists can measure rainfall, track snowpack, and run computer models that predict when and where floods will occur. But the fundamentals are the same as they were for indigenous peoples. More water in the watershed leads to higher flows. Timing is predictable based on seasonal factors. Magnitude varies from year to year, but falls within a range that can be estimated based on historical records. Understanding these patterns removes much of the randomness that makes floods feel threatening. They're not random, they follow patterns. They can be predicted, they can be prepared for. The relationship between flooding and wildfire is particularly interesting. In many landscapes, these two seemingly opposite disasters are actually linked, part of a cycle that maintains ecosystem health. In areas with seasonal dry and wet periods, the dry season brings fire risk. Vegetation dries out. Lightning ignites fires. Fires spread through dry vegetation, clearing the forest of accumulated dead wood and small trees. Then the wet season arrives. Heavy rains fall on ground that's been recently burned. The lack of vegetation to slow down water flow and absorb rainfall means that water runs off rapidly, carrying sediment from the burned landscape into streams and rivers. The sediment-laden water floods downstream areas, depositing sediment in floodplains and rebuilding ecosystem productivity. The fire-flood cycle has maintained many ecosystems for millions of years. In California, for example, wet years following fire years create massive floods that reshape landscapes. But the sediment deposition is essential for maintaining floodplain ecosystems. Fire and flood together create the disturbance regime that maintains biodiversity and ecosystem health. When humans attempt to suppress either fire or flood, the ecosystem becomes degraded. Fire suppression allows dead wood to accumulate. Then when fires do occur, they burn hotter and more intensely. Flood control through levees and dams prevents sediment from reaching floodplains, causing them to erode and degrade. Understanding that fire and flood are linked, that they work together to maintain ecosystem function, provides perspective on why attempting to prevent them entirely is counterproductive. The goal is not to eliminate fire and flood, but to manage them at sustainable levels that maintain ecosystem health while minimizing human impacts. The physical impact of floods varies tremendously based on flood magnitude and the vulnerability of the areas being flooded. A small flood might inundate a narrow strip of floodplain for a few days, moving water and sediment without causing significant damage. A moderate flood might spread several miles from the river, lasting for weeks, damaging some structures but allowing recovery within a season or two. A major flood can inundate enormous areas, lasting for months, causing significant damage and loss. The distinction between floods of different magnitudes is measured using recurrence intervals, which describe how often floods of a particular size are expected to occur statistically. A 100-year flood is one that has a 1% chance of occurring in any given year. It's not a flood that occurs exactly once every 100 years, but rather one that's large enough that, based on historical data, such a large flood is expected roughly once per century on average. A 500-year flood is one that's expected roughly once every 5 centuries. These classifications allow communities to plan for different flood sizes and to design infrastructure appropriately. A house on a floodplain might be vulnerable to 50-year floods, but be designed and elevated to survive those floods. A critical infrastructure like a hospital or fire station might be designed to survive even a 500-year flood. Understanding recurrence intervals allows proportional preparation. You don't have to protect against every possible flood. You design protection appropriate to the risk level, acceptable in a particular location. A living area that floods occasionally might be acceptable in a floodplain, as long as structures are designed to tolerate that flooding and people understand the risk. Critical services are protected to higher standards. This graduated approach to flood risk is far more practical than trying to prevent all flooding, which is generally impossible. Flood prediction and warning systems have become increasingly sophisticated as technology advances, reflecting the same commitment to understanding natural hazards that we see in hurricane and tornado forecasting. Weather forecasting allows meteorologists to predict heavy rainfall days or weeks in advance, using models that simulate the movement and development of weather systems with remarkable accuracy. Snowpack monitoring allows prediction of spring snowmelt flooding, allowing water management agencies to prepare months in advance for the water that will melt from the mountains and flow downstream. River level monitoring through networks of gauges provides real-time data on current conditions and allows short-term flood prediction, with measurements from thousands of locations all feeding into models that can predict how high a river will rise and when the peak will occur. All of this information can be integrated into flood forecasting models that predict when and where flooding will occur, allowing communities to prepare and, if necessary, evacuate. The warning lead time varies significantly depending on the source of flooding. For snowmelt-driven flooding, there might be weeks of warning as meteorologists monitor snowpack and forecast snowmelt timing, giving communities extensive time to prepare. For rainfall-driven flooding, there might be days of warning as weather systems approach, still enough time for evacuation and securing of property. For flash flooding from intense local rainfall, there might be only hours of warning, as thunderstorms develop and produce heavy rain very quickly. Even a few hours of warning can save lives, and the importance of even short lead times cannot be overstated. People can move to higher ground. They can move vehicles and valuables to safety. They can close floodgates and deploy sandbags. Communities can deploy temporary barriers and redirect water using pumps and channels. The ability to predict even a few hours in advance transforms flooding from an invisible, unforecastable threat to a manageable hazard that communities can prepare for intelligently. The technology continues to improve constantly. Satellite rainfall estimation allows detection of intense rainfall over areas lacking surface rain gauges. Improved weather models provide better precipitation forecasts. Better communication of forecasts ensures that information reaches people who need it. All of this increases warning time and improves accuracy of predictions, reducing the number of people caught unaware by floods. Beyond the predictions themselves, communities have learned to work with floods rather than against them, using scientific understanding to develop sophisticated strategies that acknowledge the inevitability of flooding while minimizing its harmful impacts. In the Netherlands, for example, where much of the population lives below sea level and has faced flood risk for centuries, the approach to flooding has evolved dramatically through trial and error and learning. Rather than building static walls that attempt to hold water back permanently, which eventually fail under extreme conditions, modern Dutch approaches include room for the river concepts, where certain areas are allowed to flood in order to protect other areas. The idea is radical in its simplicity, allowing the water to go somewhere safe, rather than trying to force it to stay where it's not wanted. When major flooding occurs, some agricultural areas are intentionally flooded to reduce the level of water elsewhere, to protect cities and critical infrastructure where human population is concentrated. This is a sophisticated approach to flood management that recognizes that you cannot prevent all flooding, but you can channel it in ways that minimize total damage. The farmers whose land is temporarily flooded receive compensation from the government, acknowledging that they're providing a public service by allowing water to spread over their fields, rather than overwhelming urban areas. The protection of human life and critical infrastructure is prioritized over the protection of any particular piece of land. The floods are managed actively, with controlled water levels and planned inundation areas, rather than pretended away or fought against futilely. This represents a maturation in how societies approach flood management, moving from a confrontational approach of trying to prevent nature to a cooperative approach of understanding natural processes and managing them productively. This approach is being adopted in other parts of the world, as communities recognize that fighting floods is less effective than accommodating them intelligently. Wildfires operate under a different set of principles than floods, but they too follow patterns that make them predictable and understandable. Fire requires three things: fuel, oxygen, and an ignition source. Oxygen is available everywhere. Ignition sources include lightning, which strikes the Earth billions of times per year, and human-caused ignitions from equipment use, unattended campfires, arson, and burning debris. Fuel is the vegetation, dead wood, and organic matter that accumulates on the landscape. The amount of fuel available, the moisture content of that fuel, and the weather conditions all combine to determine fire risk at any given moment. In a wet landscape with high soil moisture and high fuel moisture, fires will not spread easily even if ignition occurs. In a dry landscape with low fuel moisture, fires will spread rapidly and burn intensely. This fundamental relationship between moisture and fire behavior is measurable, predictable, and allows forecasting of fire activity. The fire season in a particular region is determined by the climate, the seasonal pattern of rainfall and temperature. In most regions, there's a peak fire season when rainfall is lowest, temperatures are highest, and fuel moisture is lowest. This is when fire risk is elevated. During other seasons when moisture is high, fire risk is minimal. This seasonality allows preparation. Communities in fire-prone regions know when they need to be alert. They know when to remove dead wood from properties. They know when to irrigate landscaping to maintain moisture. They know when to increase patrols and monitoring for fires. Outside of peak fire season, the risk is low and attention can be directed elsewhere. The rhythm of fire season, like the rhythm of hurricane season and tornado season, provides a framework for understanding and preparing for the hazard. The ecological role of fire in maintaining healthy ecosystems is profound and well established by scientific research, with entire plant communities having evolved specifically in response to regular fire disturbance. Many plant species have evolved specifically to depend on fire for reproduction, in ways that seem almost impossible until you understand the mechanisms. Some seeds have hard seed coats that only germinate after exposure to heat, the signal that fire has passed through and created an opportunity. Some plants have evolved to survive fires through thick bark that insulates the living wood underneath from the heat, or through the ability to re-sprout from roots after the above-ground parts are killed by fire, allowing the plant to recover quickly using energy and resources already. ice stored in the root system. Some species produce seeds in response to fire signals, essentially saying, now is the time to reproduce, because fire has created space and resources for new plants. Entire seed bank strategies in some ecosystems depend on fire, with seeds remaining dormant in the soil for decades, waiting for the heat of a fire to trigger germination. In ecosystems that have experienced frequent fires for millions of years, fire is not just beneficial, it is essential to ecosystem function. When fire is suppressed, these species disappear, replaced by fire-intolerant species that gradually become dominant. Plant communities become dominated by fire-intolerant species that could never have become common if fires were occurring regularly. Dead wood accumulates because it's not being burned. The ecosystem becomes structurally and compositionally different from what it was before fire suppression, often becoming darker, denser, and less diverse. When fire eventually returns, which it inevitably does, the accumulated fuel burns at higher temperatures and intensities than natural fires would have, causing more severe damage than natural fires would have caused in a landscape with regular fire. This creates a destructive cycle where fire suppression for a century leads to conditions where a fire, when it finally occurs, is far more severe and destructive than fires that occurred before suppression. Conversely, in ecosystems that evolved without fire, perhaps in very wet climates, fire can be destructive. But in fire-adapted ecosystems, which cover much of the world's forests, grasslands and scrublands, fire is part of the system, essential to it, necessary for its health. The diversity of vegetation on landscapes is often a direct result of fire, with entire ecosystems depending on fire to maintain the mix of species and successional stages that create biodiversity. In fire-adapted ecosystems, different species recover from fire at different rates, creating a mosaic of different age patches at any given time. Some species grow quickly after fire, producing lush foliage and flowering abundantly in response to the suddenly abundant light and nutrients. Others grow more slowly, establishing gradually as fire-adapted competitors are removed. Over time after a fire, plant communities change, a process called succession, as pioneer species are slowly replaced by competitors better adapted to the stabilizing conditions. Early successional species dominate immediately after fire, taking advantage of the open space and abundant resources. Slowly, they are replaced by later successional species that are more competitive in the absence of disturbance. If fire returns before the ecosystem becomes completely dominated by late successional species, diversity is maintained and the cycle resets. Different successional stages coexist on the landscape, providing diverse habitats for different animals. This diversity of habitats is what creates the remarkable animal diversity observed in naturally burned ecosystems. Without periodic fire, late successional species would dominate everywhere, and diversity would decline to near monoculture conditions. This is observed in real ecosystems. In areas where fire has been suppressed for decades, plant diversity often declines measurably. Animal diversity declines correspondingly, and when fire eventually returns, the ecosystem often becomes structurally simple, monoculture-like in the short term, before diversity returns. The problem isn't fire in those cases. The problem is the lack of appropriate fire. Indigenous peoples understood this fundamental principle for thousands of years. In many parts of the world, indigenous peoples used fire extensively to manage landscapes, not destructively, but constructively. They burned regularly in patterns that maintained the diversity and productivity they needed for survival. They understood fire timing, frequency, and intensity in sophisticated ways that created landscapes they could live in sustainably. When colonization suppressed these burning practices, often in the name of forest conservation, ecosystems change dramatically, often degrading into less diverse, less productive states. In recent years, there's been a recognition of the importance of indigenous burning practices, with conservation organizations and land management agencies collaborating with indigenous peoples to restore these practices. Some landscapes are returning to regular burning under indigenous management or in collaboration with indigenous peoples who understand the timing and intensity needed. The results are consistently positive and measurable. Ecosystem diversity increases. Wildlife populations increase. The landscape becomes healthier and more resilient to other stresses. The productivity of fire-adapted ecosystems is remarkable. Grasslands in Africa that burn regularly support enormous populations of grazing animals and predators. Forests in many regions that burned frequently before suppression supported greater bird diversity and more productive ecosystems than the dense, dark forests that developed under fire suppression. The forest structure in naturally burned landscapes is different from suppressed forests. Naturally burned forests often have an open canopy with sunlight reaching the ground, diverse understory vegetation, and complex structure at multiple levels. Suppressed forests often become dense, with a closed canopy, minimal understory, and simple structure. The open structure of naturally burned forests allows sunlight to reach plants on the ground, increasing productivity. The diverse structure provides diverse habitat for wildlife. The naturally burned forest is more resilient to insects and diseases because the stressed conditions of overcrowded trees are absent. All of this means that fire, properly used in fire-adapted ecosystems, is not destructive but productive. It maintains the ecosystem's ability to provide resources and habitat. It prevents the catastrophic conditions where extreme fuel accumulation leads to fires so intense they convert the ecosystem entirely, replacing forest with grassland or leaving barren soil. The goal in fire management is not to prevent all fire, but to maintain a natural fire regime, one that includes regular smaller fires rather than infrequent catastrophic ones. Wildfire prediction and management have improved as understanding of fire ecology has advanced. Fire danger rating systems use measurements of fuel moisture, temperature, wind speed, and humidity to calculate how rapidly a fire would spread if it started. These ratings allow forecasting of fire danger, alerting communities and land managers when fire risk is elevated. When fire danger is high, certain activities like equipment use that could spark fires are restricted. Prescribed burning is scheduled for times when conditions allow controlled burns that reduce accumulated fuel without becoming too intense. Lightning detection networks identify where lightning has struck, allowing quick response to any ignitions. Remote sensing satellites detect active fires, allowing rapid dispatch of fighting resources. All of this infrastructure exists because of understanding that fires are natural, that some fires are essential, but that uncontrolled wildfires in heavily populated areas or where fuel has accumulated to dangerous levels need to be managed. The goal is not fire suppression everywhere, but rather smart fire management that uses fire as a tool where appropriate and suppresses fire where necessary. This represents a significant evolution from decades of fire suppression that led to fuel accumulation and catastrophic wildfires. The recovery of ecosystems after wildfire is one of the most remarkable natural processes to observe. Within days of a fire's passage, plants that were killed above ground are beginning to re-sprout from protected roots. Annual plants are germinating from heat-activated seeds. Insects and other animals that survived in soil or fled the fire are returning. Within weeks, the burned landscape is already beginning to green again. Within months, plant growth has accelerated dramatically. The loss of competition from other plants, the abundant nutrients released by the burning of organic matter, and the return of sunlight to the ground create ideal conditions for plant growth. Productivity can be higher in the first few years after fire than it was before fire. Animals that feed on plants and predators that feed on those animals respond to the increased productivity. Wildlife abundance often increases after fire. The ecosystem is not destroyed by the fire. It's transformed temporarily in ways that often increase productivity and diversity. Over time, the ecosystem matures again, develops taller vegetation, becomes more complex. Then fire returns and resets the process. This cycle has maintained ecosystems for millions of years. The recent suppression of fire is very recent in geological terms, just a century or so in most places, yet it has dramatically altered ecosystems. The recovery of natural fire regimes, which is beginning to happen in some places, is showing that ecosystems respond positively when fire is restored. The relationship between humans and fire is ancient and complicated, spanning from the earliest human use of fire for warmth and cooking to modern landscape management strategies that recognize fire's ecological necessity. Humans have used fire as a tool for controlling landscapes for hundreds of thousands of years, with evidence suggesting that fire was used deliberately to manage hunting areas and control vegetation long before agriculture developed. In many regions, human use of fire shaped the vegetation and animal communities in profound ways. The grasslands of South America, Africa, and Australia were maintained by frequent burning, much of it human-caused or human-influenced, creating the distinctive savanna ecosystems that supported enormous populations of grazing animals and the human hunters that depended on them. When colonization disrupted these burning practices, often in the name of forest conservation that didn't understand the ecological role of fire, forests expanded into grasslands, dramatically changing the landscape and the animal communities it supported. The loss of fire was ecologically disastrous in many regions, reducing biodiversity, reducing wildlife populations, and creating conditions for catastrophic fires when burning eventually resumed. Now, with growing recognition of fire's importance based on scientific understanding of fire ecology, there's a movement toward restoring fire to appropriate landscapes. This includes support for indigenous burning practices, prescribed burning on public lands where controlled burns can reduce fuel and restore natural conditions, and greater acceptance of natural wildfires where they can be safely allowed to burn without threatening human infrastructure. The knowledge that fire is not purely destructive but rather essential to ecosystem health is transforming how we approach wildfire management at every level. Rather than viewing any fire as a failure to be prevented at all costs, we increasingly recognize that some fires are necessary for ecosystem function, that preventing all fires leads to conditions where catastrophic fires become inevitable, and that working with fire, using it where appropriate and managing it intelligently where necessary, creates healthier, more resilient ecosystems and ultimately reduces human suffering from wildfires in the long term. Understanding both floods and wildfires as parts of natural systems that maintain ecosystem function and diversity provides profound perspective on living with natural hazards, a perspective that emerges from scientific knowledge, but also from wisdom accumulated by peoples who lived with these processes for millennia. These are not random disasters imposed on the world by a chaotic universe. They're normal operating mechanisms of ecosystems, essential to the long-term health of the planet and the continuation of the biological diversity that makes Earth habitable and beautiful. Communities that live in flood-prone or fire-prone areas are not living in deficient locations, at least not from an ecological perspective. They're living in some of the most biologically productive and diverse places on Earth, in landscapes that support extraordinary abundance of plants, animals, and opportunities for human life if we understand and respect the systems we're living in. The productivity of floodplains, the biodiversity of fire-adapted ecosystems, the recovery potential of landscapes after both floods and fires, all of this speaks to the resilience of natural systems and the ability of nature to maintain itself through cycles of disturbance and recovery. When humans work with these systems rather than against them, when we maintain natural flood and fire regimes rather than suppressing them entirely, we live in more sustainable and ultimately more secure relationships with the natural world. The acceptance of floods and fires, the understanding that they're necessary, the recognition that recovery is reliable and often results in greater productivity and diversity, this transforms how we think about natural disasters. They become, in their way, processes of renewal, expressions of how the Earth maintains balance and supports life. This perspective offers peace, not because it eliminates natural hazards, but because it places them within a comprehensible system where they serve purposes we can understand.